So I want to welcome you all to the first insider trading talk of this season. So, insider trading is meant to be, a lecture series within a lecture series that's meant to be far more informal, even though we have the seats set up as formally as we do for the nighttime lectures. The lectures are meant to be a little bit shorter, a little bit more informal, and more opportunity for question and answer. So if last semester's insider trading focused on the young practitioners on our faculty, this semester we're focusing on the Totalization Studios initiative. As you all may know, the Totalization Studios fulfill the NAAB Accreditation Board requirement that all accredited architecture degrees include what they call a comprehensive studio that demonstrates, and I'll quote from the NAAB, a fine literary source. The NAB Comprehensive Studio demonstrates an ability to produce a comprehensive architectural project based on a building program and site that includes development of program spaces, demonstrating an understanding of structural and environmental systems, building envelope systems, life safety provisions, wall sections, building assemblies, and the principles of sustainability. So we here at the RSA don't really believe that comprehensive is viable as an agenda for a semester-long studio for a student, and see this as an opportunity to try to recalibrate that obligation in a way that's maybe more productive. And so that's why we've put together these Totalization Studios as an effort where each studio is focusing on one aspect of that mandate, and the idea is that the 4 studios in collaboration at certain points in the semester, and this is one of them, will allow the students to get that broader, quote, comprehensive view of architecture. So it's an initiative that we're trying to take back to the NAAB. It's one that has been very exciting to our alumni, and we've actually received funding to fund these studios for the next 5 years at a level that will actually bring the consultants in for even longer periods. And so that will be announced later in the semester when that funding is finally actually secured. But it's sort of nice to see the validation of this experiment already coming to fruition. So today we have Mark Malekshahi, who was falsely advertised as working at Plus Group, which was true at a moment, but is no longer true. He's now at Bureau Happold. He is a professional engineer, a designer, lead engineer, and project manager who, before working at Bureau Happold, worked at Plus Group, and before that at Cosentini. He's been involved with some of the most significant architectural projects in the U.S., I would say, wow, it's really raining, over the last decades, including Frank Gehry's Lewis Library at Princeton, the Wiley Theater that many of you have seen in Dallas by Rex and OMA, and the Sana Toledo Museum of Art, which actually just in my seminar we were discussing in the context of Logier, how one can actually put HVAC in a glass museum. So there's a group that's particularly keen on trying to figure that out from you today. But we welcome you here for this talk, but also for the Totalization Studio. So thanks very much for taking the time to come.
Thank you so much. Thank you. Is this the time to turn the... This is the time. And what is this for? Just so I know.
That's just for the video recorder.
Okay. Thank you for inviting me. I guess I'm the starter of the series. Probably for some of you guys, or for most of you guys, the least relevant or potentially relevant subject out of the 3. But I think that ultimately, once the building is done and finished, it's probably the one that may or may not give you more headache. And it would probably last quite a while, potentially after that. So I think that the importance of the building systems becomes more relevant in the modern design as we go on, especially designing for areas that are basically not necessarily prone to see a modern design, somewhat exposed design. So let me just start with talk to you guys a little bit about overall what is an integrated design really mean for all of us as a design team, not just for architects, but it's really start with to me as a framework for guidance to move forward. Looking at the building program and look at really overall local climate and restrictions that we really need to deal with as a design team, not just basically as a sub-consultant to the team or to the architect. Evaluating really the overall energy sources that are available for us, and basically look at from the really the interest of the client, what are the really preferred source of energy, and based on the budget that is available, how do we work with, and how do we really integrate all of these issues with local practices. These are really all came somewhat head-on to some degree or another at earlier stages of design, if you really need to take a look at that integrated design and see how that basically would work out with a typical building or atypical building in case of Wiley Theater or any other highly integrated design buildings. From our standpoint or from your standpoint, one may think that basically comfort is all about temperature in the building and getting the humidity out, especially if you happen to be in areas like Houston or in my recent travel in Doha, which is basically intolerable climate for this type of building design. But once you really get beyond it, a comfort design has many different aspects, and depending on the building, depending on the program, there are different things that basically one building has to be, one design has to be sensitive about or not, and it may involve many things, noise or type of basically use and areas that basically are we need to take advantage of. Integrated design may vary one degree or another within a building and design, but just start by the fundamental questions that we as a designer get involved with and pose really from our standpoint to the design team. And these are basically, we need to take a look at the indoor design conditions, the nature of what is really the program that produces or takes the heat out of the building, or produce basically the heat of within the program space. How do you basically conceive of providing air conditioning or comfort design for the building? And it goes on to that. How do we construct it? What are the opportunity for construction, and how do we really maintain it? What type of source of maintenance programs are available for the end user after the design is done? So basically, the integrity of the design remains intact for years to come. For a typical construction, at this stage is somewhere about 20, and some buildings needs to basically be functional, good functional building for over 100 years at least. And once you look at that, and of course, I think that we're all familiar with the fact that there are many different building types, and each one of them really deserves their own attention, and not necessarily they all function and work similarly. From the building system standpoint, the critical issues that we need to concentrate on or look at is at this stage is from the comfort standpoint is really the thermal, the visual, the acoustics. Probably from the user standpoint, thermal is a much more relevant, or acoustic probably is more relevant. From the architect standpoint is the visual part of it, and obviously for the owner or the client, really the energy standpoint, how much of if they tend to be end user as well, how much of energy consumption, energy value the building has later on, and what kind of a cost it really has for really operation of the building. So these are all critical issues to really consider for the early stages. And then typically you at the concept design, you get to see a vision that basically is posed by the designer and proposed for the building. And it's really important to understand and to see how this vision, like for example, this one was the competition rendering from Sana for Toledo Glass Museum. It's really a very transient glass building. This is the vision that the architect really put forward for the building at the competition, and obviously it's very conceptual, and we basically were tasked to see how much we can really make it a true design for a place like Toledo. So it's important to understand all these issues, and the overall fundamental task for us as a building engineer, building system engineers, is really obviously the concentration of it is dealing with ventilation, heating, cooling, and public health and life safety. But obviously there are some items like lighting and acoustic that at one time or another becomes also an issue for us. Just to give you, I don't know to what extent you're familiar with, but I've come across many studios in a way that students concentrate more than often on, how shall I say it, just the program area design, not realizing that a building, like any other functional organism, needs all the background system for it to function. And it could take up to 10%, 15%, depending on the design program, of your overall area of a building. It's substantial. It's 15% once you really design your building or propose your building to the client without understanding it, becomes an issue where to really fit all these elements and design to your building without really at the earliest stage looking at it. So it's important to keep in mind that a successful building design, it really takes all these areas from your program, and it's important not to lose track of it. Or basically, in case of, for example, again, Toledo, if it's a totally glass building and it's visible, where do you really anticipate to house all this background equipment? Couple of issues to look at the earliest stages from our standpoint is really to look at how do we make the decision about certain things. And fundamental decision of one is really if how do you supply heating and cooling to the building, and these are all issues that becomes fundamental questions at the early on, and it's not a decision purely made by us or you. It's a decision that is really would be successful to make it by a joint effort with the client as well, because obviously ultimately it's a long-term issue that they have to deal with. So once you look at the system and see if it's an all-air system or if it's a hybrid system, it would impact your overall design, and depending on where do you want to go or where do we want to go, and what are the available spaces or areas, potential areas in your building, in your design, it impacts the selection of the systems. Fundamental question number two, if the building or the design that you have is somewhat exposed or not exposed structure. It will impact basically how do you incorporate your mechanical system into that exposed structure or concealed structure. It also it's important to understand if this exposed structure or basically interact with outside, to what degree, and what are the basically ways to mitigate that. If it's basically similar to most of the modern airport design, for example, at this stage that you see where the steel goes from inside to outside in an area where the thermal gradients within a day or within a season is very extreme. Case of, for example, Doha, or areas where temperature in the day could be reaching over 100 degrees Fahrenheit and at night drops down to 50 degrees. It's important to understand some of these elements and how do we mitigate that. So an overall integrated design, it's important from the beginning to understand what are the possibilities and what are the potentials. Decision number 3 that we usually pose and look at earlier stage is really if there is a potential for natural ventilation or if there is any possibility there. I've come across many times working with the European architect where basically they're very comfortable based on their practice in Europe. There is a much wider band of tolerance as far as the thermal comfort is concerned within a building, and most often they're very surprised with your American designers where basically a total air conditioning system is always offered, and they always tend to gravitate toward a more natural ventilation design, and that's basically we need to take a look at and see what are the potential and possibility for natural ventilation and how it basically impacts not only the internal design of the building but also the external design, the envelope of the building. And each one of them would provide certain amount of answers and questions. Just getting into a little bit nitty-gritty of the overall building systems. It's important to understand that overall there is a substructure and there is a superstructure for mechanical or overall building system design. The infrastructure really involves with energy sources and where you get that energy sources, what type of energy sources are coming into the building, and each one of them will impact your design one way or another. It impacts the infrastructure of the building, areas that you may not necessarily expose or show it, but it ultimately becomes part of the building area that impacts your program. So these are some of the, just a sample of very basic point of incoming service, point of things that you need for the building, and at one stage or another it may become very critical and may impact not only your building layout but also some of the program areas. The other thing that I wanted to basically bring to your attention is that it's important from the early on, once you have the model or once you in case of, for example, this building, this is a Corcoran Gallery of Art design that I was involved with Gary partnership, and we produced a CD document and just never got off to the construction. But when you look at a building like that, a design like this, it basically tends to you need something that is basically a system that is totally concealed. More than that, it really, when you look at the facade of that basically is curvatures, curvilinears, and it has very clear pieces in here. It's important to understand where it's built, what are the parameters for it, and what are the pitfalls for it. There was a similar design to this by Gary. I think it was in one of the university. I forgot the name of the university right now. It was a business school where basically the facade subject to really extreme temperature and rainfall like this, and then basically temperature drop created huge mess really for the post-construction as far as ice build formation building in here and dropping on the pedestrian area. So it was important to basically look at these things and see how the actual integration of the systems impacts the facade and impacts the overall exterior design of the building. In case of Wiley Theater, for example, the facade and the design was such that would not provide us with any opportunity for integration of the mechanical systems, louvers or whatnot in the building. So it for us was important to understand how the building is conceived and what are the criteria as far as the cooling, heating systems for the building, and what do we need to basically consider. The other thing is that from the program, we were looking at different issues, solar panels, radiant systems, and whatnot, and each one of them basically were examined at the earliest stage with the designer to see what are the opportunities that for each one of these buildings should be considered. Once you look at these things, there are a lot of environmental issues that needs to be looked at, and ultimately one or the other of these items in here becomes things that we have to overall look at this and examine with the designers. It's one or the other becomes very critical for them. So all this will be considered, or we consider them with the designer at the earliest stage, and then trying to basically really communicate with them the main factors, and try to basically utilize and work with them in earlier stages what it could be really potential for integration of the mechanical system, MEP system, into the design. It's important to communicate some of these in order to early on to basically help not only shape the design and the elements, but also help increase the efficiency of the building. Then later on in the later stages of the design, it basically we again evaluated and go through it more thoroughly to make sure basically we actually implement some of this. This is a snapshot of Genzyme building at Cambridge, where basically original concept of natural ventilation into the building was studied and looked at, and basically we followed it through to make sure that basically it gets incorporated into the glass facade. The other thing that I just wanted to basically go in brief about it, as it becoming more and more an issue, is really how do we incorporate and approach really a sustainable design toward the buildings. And it's for us, it's important not to make it as an add-on to the building later on, but look at it from the earliest stages and start from overall elements that are helping to basically start a high-efficient passive design, and then add basically potential efficiencies to the system as is possible, and then what are the basic potentials for renewable sources that we can add to the building, add to your design. So I think that it's important to understand the building, the high efficient building should really start from its actual inherent architectural design, and then move forward from to look into a high efficient system, and then to renewable. So we look at from the beginning, from the benchmarking and modeling of the system for energy modeling. What is the base design for the area? What is the base design for the overall for the region, for the locality? And then add the passive system, or look into the potential passive system for the area. For example, in cases like design in the very hot and dry climates, such as Middle East, certain area of Middle East, it's important to understand the passive design and take advantage of it as much as possible. External shading or overall envelope design that basically provides very, very high design is really critical, because obviously, although the cost of the energy consumption is low, but the overall energy consumption is high for a typical building. So ultimately, it becomes an issue. Then, obviously, we'd like to look at the active design elements to reduce that overall energy cost and provide a high efficient system as much as possible, and then look into the renewable sources of energy. These are all elements that ultimately would drive the overall consumption of the building down as much as possible, and obviously bring it down to the goals beyond the future 2030 energy model. As far as the relevant the climate controls for the building design, obviously, once you look at the building, there are different categories and different requirements. Just as a note, if you look at a historical preservation design or exposure structure, it's one way to look at it, and those are, there are sensitive issues that needs to be considered. While if it were basically a modern exposed steel structure, there is another way of looking at these things and provide us with an opportunity. So it's important to understand how do we take care of the climate control in a building and what type of building you have. In case of Toledo Glass Museum, when we started the concept design, we early on understood that basically it's a building that is totally exposed, totally glass building, and it needs to behave differently in summer season versus winter season. And working with the architect on that building, we start developing potentials and looking at the building in a way that helps us both to integrate design as much as possible from a mechanical standpoint, while making sure that building operates properly. One of the things that we start to look at is really the envelope. Architect wanted to have a very fully glass wall, and obviously for a building that is a museum has to set the standard and meet the standard of Smithsonian for the humidity control. So a single layer of a glass wall would not give us that opportunity, would not give us that control one way or another, however way you look at it. So what we looked at is really creating a buffer zone for the building. I mean, the buffer zone that basically provided opportunity to basically isolate the galleries from the outside, and while basically treating that galleries and keeping it isolated from a very cold temperature, -3 degrees at time in the winter time, with a basic humidity climate control inside at 55 degree, 50% relative humidity. It's a very challenging task. But again, we put all these concepts and work with them in order to make sure that everybody understand what are the design criteria and how we can basically mitigate and incorporate the design elements into their design, so it doesn't become an overall extension, and it becomes part of the design. So once you look at just as a start of a evaluation, a building typically basically has certain design parameters. For the temperature is basically roughly about 60 to 80 degrees, and for relative humidity is somewhere about 20 to 60% relative humidity. It's and the source of humidity, of course, it becomes very critical. It's either indoor, it's the inside of the building is human and planting in the building, or from the outside is really outside air, and how humid the outside air is. So those are the issues that just wanted to point out to you guys. And the typical building that we used to design, or ideas that we used to design, was to provide a total isolation of indoor versus outdoor. That's usually the approach that we used to take as far as the design building is concerned. But as we're getting more involved with the high cost of the energy consumptions for the building, we tend to look at buildings in a way that basically from a tight area for climate control to a much wider band of area where basically climate control is of a relevant, and trying to basically work with the architect from the early on to work with the programmatically how to lay out the areas that basically work with these parameters better, so we can work with them in a way that reduces the overall energy cost of the building. Just again going to the example of Toledo, we had basically a double wall glass areas and with a cavity in here that worked as a buffer zone for our climate control, and it not only provided a climate control for the building, but also provided areas to basically, in places like this, which was a shop area, to basically isolate that area from the outside. The other thing that we were working at Toledo was the challenge of one side of the building. It's really overall galleries that needed to function with based on the Smithsonian standards of 50% relative humidity. But the other side of the building was a functioning hot shop area, and these two programs basically are very much against each other. And within the inside of the building, we have this area, what they call the foyer in here, which is really somewhat of a buffer zone between one program and the other program. But overall, the hot shop area in here was providing a lot of issues for us as far as the radiant heat concerned into the adjacent spaces. And we need to basically work very closely to see how we can mitigate that from the energy standpoint and also heat transfer. The other thing that was really of a concern for architect is really the visual aspect of the building communicating to the outside. It was very important for them to make sure that the building is a full clear glass building where basically outside visitor from outside can see what's going on inside the building, how the shops and teaching shop areas can basically be exposed, and viewers can see what's happening from the inside. And the other thing is that obviously forced us to locate all of our elements out of the way into the basement and trying to basically serve all the areas from the basement level. This is just bear in mind that I'll get back to this later on, but a clear glass building that we had in here didn't provide us any opportunity for an area such as hot shop that has those kilns and element in there can produce up to about 1750 degree of Fahrenheit heat in that area. So it's something that basically had to be really looked at. It's not a very easy design task for us, if I can say that. One thing that we used at later stages of the design was really to take advantage of the CFD analysis and CFD modeling to really validate our approaches to the design. We studied along with Transolar engineers really the various schemes for the ventilation of the glass in the ventilation of the gallery areas, and how do we basically mitigate the temperature gradients across the gallery versus to the outside. And this is just a snapshot of one of the final studies where basically in order to minimize the overall impact of the mechanical system in all clear glass gallery area, we were supplying from the floor as a floor displacement ventilation air, while we had basically introduced radiant floor and radiant ceiling panels in here in the cavity area to reduce the overall ventilation air and reduce the amount of air that basically needed in the cavity to mitigate the temperature gradient in here to absolute minimum. Otherwise, this whole area would have been basically a wind tunnel as one of the early proposals that we looked at. So we went through different iteration of the CFD modeling to basically get to this. And ultimately, it showed basically just as a snapshot of one of the thermal gradients to basically how the temperature along the glass outside versus inside and the internal temperature inside the gallery behaving in that mode. Another example that I just wanted to bring up, this is the competition for National Museum of African American Cultural Heritage with Delos Scofidio. We got involved with the competition, and as you can see, it's a design that basically has a structure, almost fully enclosed structure, but with the skirt of a glass over basically coming down and enclosing the building in that area. And that glass skirt is basically, it's somewhat of really high and big surface area for places like Washington to basically make sure that it's really staying clear and clean as far as condensation is concerned. So again, with them, this is one of the examples of really working with the designer from earlier stages to make sure that how they program the building and where they put their programs, so we can basically take advantage of the tight areas or look at the galleries with very tight band in the innermost portion of the building where it's much easier to control it, and then bring it out to the loose areas where outside it's basically this area within the exterior of the building can be comfortably met with the outside with just a sheer single pane of glass. So there were other issues that basically, as part of the program, we had to consider and looked at it in a way that basically how do we integrate the building where basically it kind of operates nicely to the outside without really impacting the glass facade. So, in this one we had also challenges of that was put forward from the competition to how do you really integrate the sustainable renewable source of energy in here, and we integrated some solar panels on the top of the building, and we didn't win the project, but it was actually a very nice competition. This is just some example of hiding some of the renewable sources is always a challenge for the building, and it's important to understand where are the opportunities for us. Another example that I wanted to just bring up was actually sometimes you end up working with a building that are basically it's not a existing design, but it's really working with renovation of the building. And it's important to understand how the building was constructed, how the building was really conceived design-wise in order to implement your changes and trying to basically make it better. This obviously, I don't know if you guys know about it, but it's a GSD built in 1970s with a lot of problems that, from what I know from the original, some of the designers who worked on the building, they knew all along that it's problematic, but they let it go at that time, and they had to basically deal with it for generations, and the student had to live with it for generations. One of the things that I found out basically, all these truss covers in here were fiberglass. Fiberglass that basically loses its value, whatever it had lost. To begin with, it didn't have much of a value, but throughout the years, it basically lost its value. And what it does is basically that truss cover the main trusses are sitting in here, and because this truss covers really didn't have much of a value to begin with, created an environment in Boston. I mean, you can imagine in Boston, very cold environment. These trusses becoming basically transfer elements. So what they were doing throughout all these years, or they're doing right now, is basically at wintertime they're becoming basically cold steel radiant panels, and they basically drawing. Actually, if you hold your hand in the bottom part of here, when basically it's reachable, you can feel basically air is coming down. It's that much noticeable that you hold your hands around it, you feel the cold air is just basically coming down from that element, and all it does is basically, in the wintertime, drops the air right on the what they call the lower dish students area, where basically student on this level in here, they tend to sit with full gloves and hat and everything all throughout the winter time, and while the student on the top dish area basically have to be with t-shirts. It's a very interesting area to look at. The whole design of the building was by itself, it's a challenge, and let alone the system that were available back then in the 70s didn't really help it, and the design that they put in there didn't help to mitigate this whole issue of a high stack and thermal gradient transfer from bottom to the top. So that's where I basically was saying that the designer knew what's going on, but they just didn't really deal with it at that time. So we got involved with the design about 2 years ago, before the market crash, and it was supposed to be basically one of the main infrastructure upgrading of the building, but and we did a construction document for it, but it's basically right now on hold. We tried to basically reverse the system in here and to basically help to mitigate some of these issues of that I highlighted in here as far as the climate control is concerned. The other thing that we talked to them about is really analyzing and reviewing really what is the climate control and what is the comfort levels that we need to achieve. It's important for the client to understand there is a band that at time, depending on the program and depending on what you're really trying to achieve, could be really this point in here, if it's a museum and if it's object-oriented, or if it's a certain design program. Sometimes it could be a little bit looser. There's a more tolerance in, for example, building designing for the students, or if it's, for example, a residential building. So it's important for the client to understand that whether they have to really tolerate this type of close climate control, or they can go basically a little bit beyond it and trying to basically hit something that is a little bit more comforting as far as, and has a wider band of control. So one thing that we talk to them about it is really discussing really what is the important things, and as far as the climate control of the space is concerned. I don't have the snapshot of existing system, but it's a very similar, very simple system. It's basically overhead supply of the air, single unit, dumping air from the top in here, from the diffusers, and then the returns is right here going back into the air handler, existing air handler in here. So what it does is basically the mechanical system is just, imagine, is trying to work as hard as it can to basically cool off or provide a climate control for the overall space, whether it's, for example, 1 foot from the floor all the way up to the ceiling height, which is about 18 feet or so, or 10 feet, depending where you're standing. So it's by itself that the system is really trying as hard as it can to provide cooling or heating for this large area, which is really glass on 3 facades in a way. It's and the facade itself at this stage is very inefficient. It has over 2 air changes per hour of infiltration. So you can imagine, however way you're trying to mitigate that, still it's a problematic building. What we did and what we could do was very limited. We looked at various system alternatives for it. What I wanted to do is provide a combination of radiant system in the ceiling with a minimal ventilation area here. But one of the things that came very early on to as part of the study became known to us is the fact that in order to implement any system on the ceiling of the building, we had to incur over $1 million worth of structural implementations, upgrading. So a system that could have worked really easily and nicely with the building as far as the mechanical system is concerned was so costly on the structure that basically it was not a feasible option. The other thing that I looked at was basically a underfloor or floor displacement system, but the impact on the overall exposed structure construction of the building was such that the building would not allow it to happen. So we end up with a somewhat of a happy medium of basically providing a system that provides air from the ceiling at a lower elevation, but trying to implement such that basically we take the returns into the under what they call it, under the dish area, and provide a reverse direction of the air. So we break down into that overall movement of this high stack air movement that basically takes the heat, takes the hot air all the way up in here and provides a very uncomfortable situation in the upper level. So it's a basically just imagine that it's a remedial integration of a better system into this existing design. So sometimes just wanted to make sure that you understand it's not everything optimal, but it's something that basically we have to work with what is possible for us. Couple of issues as far as the integration of the interior design element. It's important to it's not all about energy, it's not all about efficiency of the basic building system, but it's how you we can integrate that into the internal of the building. And it's important to understand from the architect what are the concerns, what they can tolerate and what they cannot tolerate. In Toledo Glass, obviously the clarity of the facade was one issue, but they were very concerned about overall what they see on the floor and what they see on the ceiling. And the other thing obviously for sauna, everything has to be minimal, and that was really, as far as the visual is concerned. By putting radiant system in here and in the ceiling, we reduced the amount of overall ventilation air and airflow to minimum. So basically, the overall design of the diffusers and airflow system was basically reduced to very small pieces. I don't know if you guys can see that or not, but there is just a very small radial diffusers every now and then in the cavity area, and the rest is fairly clear. The other thing that we looked at in here, obviously in the shop area, where as I mentioned before, it was a very intense heat producing area. Fully air conditioning was not really an option. From the energy standpoint, it was very costly, and from the overall visual standpoint of integration of the diffuser for all air system in here would have cost basically the whole ceiling to be nothing but just a huge diffusers. Just as a point, in the areas like in front of the shop, in front of the kiln area, the temperature on the floor was somewhere about, without any mitigation of the temperature, was about 170 degrees on the floor from the radiant. So it's a practicality of working over there that forced us to look into a bit of in this area. We introduced heat recovery radiant system underneath of the floor to constantly take the heat away from the surface areas in the shop, so it doesn't radiate back to the users and occupant in here, and then take the advantage of this heat recovery in here to basically put it back in here into the radiant system of cavity area to basically heat the external surfaces of the galleries areas, so we don't have condensation. So it was really at the end is really taking the advantage of the moving heat from one place of the building and using it for the other side of the building, so we can not only meet the energy code but also the overall intention of the designers. The other challenge that was in the Toledo Glass Museum is that, as I mentioned to you before, the overall structure of the building, the roof level, including the structure, was 20 inches. Out of that 20 inch of the roof area, 14 inch at times was for the girders, because if you look at the building structure is such that basically, I don't know if it's shown in here. No, it's not there. Well, if it's there, it's very hard to see it. But the columns in the building are solid steel column, 4-inch thick. The whole entire building is sitting on these matchsticks, basically. And obviously, none of them are in the program area. They're all hidden inside the walls or in the cavity area. And because of that requirements of a clear gallery area from the structure, you can see that the main girders are acting where they basically have to go in order to basically hit those columns down where they need to. The challenge that posed to us with that 14-inch structure and really 6 inches of available space underneath of the structure was two things. One was the fact that the glass expansion back and forth between underneath of the structure and the ceiling was taking away 3 inches out of the whole available space. So there is only 3 inches left for all the services that needs to pass between the roof down into the basement, where basically most of the mechanical system there. The things that were basically was left for us to look at once we reduce all the mechanical system to the basement and eliminate most of them from the really overhead system was really the roof area, was the overall roof drainage system, which is a gravity system, and you can imagine it needs to travel based on the pitch of the pipe to where it needs to be. And the second one was really the fire protection system. Fire protection system is a pressurized system that basically you can have a little bit easier way of dealing with it, but gravity roof drainage system needed to be really looked at how you run it and pitch it, so we don't end up being below the ceiling level and taking it so in the places where we can take it. So we again did a CATIA 3D modeling of overall roof area, and I think this was it took us about 12 modeling to make sure that all the pipes passes in the right place, where basically we're not impacting the overall structural elements while we're passing through the structure into beam cuts or beam notches where it's allowed. And we had to move pipes back and forth in the area to make sure that basically the structure stays intact as far as the load is concerned.
Mark,
Go ahead.
can you show us how many places are there? You talked about all the problems in the horizontal plane, but vertically, where are the chases that you could bring all those systems up from the basement? Because if you only have 4-inch steel solid,
the chases that provided to us, you can imagine there's very few solid wall in the building. Those who have looked at the building or visited the building, there's 3 solid areas in the building. One around one of the exhibition, 2 around 2 of the galleries, and 1 around this area, which is a shop area. And we had to basically make sure that the pipes, and obviously this is a very large roof, where basically because that guideline of the 20 inches of the thick solid area available for all the roof structure, roof was very flat, inverted pitch. But the inverted pitch that was allowed for us was somewhere about, I think, 3 or 4 inches at maximum. It's a long-time memory. So we had to basically break down the entire roof area into the areas, square areas, to basically take the water out, area of the trunk. So we had, I don't know, over about 12 or 16 roof drain locations, and they had to travel within the area to these solid walls and then go down into the basement. So the location of the travel was important, because as you're passing through this and you're pitching down, you may start from one point in your travel, but then as the pipe goes down and travels, you're heading the steel in places that is not allowed. And depending on how close you are to the main girder, and if it's not allowed, then we have to move the pipe over and hit the beam at places that basically would notch out or allow the beam to basically go down. And I wish I had a picture of the actual construction of the structure, but it was a quite interesting thing that had to be worked out. But we had a very limited areas for the pipe to basically go down. One was in this area, one was to this area, and the other one was in here, where basically the solid wall was available for us to take it down. There was also another plate in here, the shear plates in here, that we extended the two ends of the shear plates, created chase for the roof drain to go down. But I never came across one of my design where basically roof drain was so critical to the overall design. Another example of overall integration of the design was this is Wiley Theater lobby area. I don't know if you can see it clearly or not, but the design was such that basically it's a pure concrete exposed structure with nothing to be shown in this area as far as the mechanical system is concerned. When I say mechanical, I don't mean it just mechanical. Keep it in mind, electrical, everything had to be basically concealed. And we integrated a radiant system in the floor for heating and cooling. And as far as the ventilation is concerned, this is a area where basically actors and performers can go from one side of the stage to another side. It's what they call a vomitory. In front of it, basically, it's a double ventilation panels that all the air for the lobby ventilation was integrated into that double ventilated panels, where this is just basically ventilating air into the lobby area, and then from the seating area would take the air out into the basement. But what I wanted to show is that really the challenge of integrating all these elements into the structure of the floor slab, heating, cooling, electrical, and whatnot. So again, from the early on, from the vision that the architect had for this area, it's important to understand what the interior space needs to be and how do we basically work toward that. And of course, just a couple of elements that we utilize for the various part of the building in order to reduce the overall requirements of ventilation and flow of the building was, in this particular example, was radiant system. So what we created is basically as much radiant panels, incorporating radiant panels into the lobby and into the performance area to take the overall heating of the space out, the overall heat rejection of the space out, in order to reduce the ventilation.
Those embedded in the slab?
No, those radiant panels that I just showed you right now, these are actually exposed panel. But what they, for the overall hall area in this particular design, gave us the opportunity in here, which is an open ceiling area in this case, where basically we embedded the radiant panels underneath of the the stage gallery, walk-in areas, galleries on the top. So underneath of those galleries, basically they have radiant panels that takes care of the glass facade in Wiley Theater. This is one of the rehearsal areas. Again, in here we introduced and we incorporated radiant panels in the open structure between the light areas in order to reduce overall ventilation airflow requirement for the building. And keep all the walls and the ceiling and the floor as clear as possible. But it was a very interesting integration of the systems into overall building interior design. A couple of more snapshots of Wiley Theater again. This is the shot from the floor area. Again, radiant floor panels and ceiling, and trying to basically show the actual some of the radiant ceiling, chill beam in the area. This is a smaller version of an overall glass building. It was an addition between two of the building in Columbia University. It's a student center, and basically it's a glass box. You don't see the glass ceiling in here because we provided a perforated glass panels in the ceiling to reduce the overall solar load into the area. So what it does is basically provide as much view as possible, clear view when you're standing underneath of it, but it cuts back as far as the solar load is concerned in the area. And then the overall facade was basically two moving glass panels that provided the design with opportunity of natural ventilation when the autumn and spring when the weather is good. But what is important for us was the fact that when it's closed, it had to really behave like a fully enclosed glass structure. So just to kind of finish it off, just as I'm sure you're all aware of it, but these are up to now what we talked about. It's really, most of it was elements for high efficiency design system, and just something that is becoming more and more important for us as far as the really integration of the high design building is really some of the overall active renewable sources, and at times it's becoming an issue for us as far as integration of it is concerned for the design, and it's important to understand that from the early on if we do have opportunity for it or if we do have a mandate for it. If building, just as example, in building design in Saudi Arabia or in Qatar, where basically we have to have the mandate of meeting a gold LEED building or silver LEED building, and it has to be somewhat between 10 to 20% above ASHRAE benchmark. It's very challenging to really reach those percentages with just overall passive or active design systems. Ultimately, it's important to introduce renewable sources even in those areas, as cheap as energy sources are. But in order to make sure that these elements are not just the tag-along pieces all over the building, it's important to understand it from the early on and trying to incorporate it into the building. And of course, for an active design building, we really the concentration is on all the commercial type of building, not just a highly designed building. Just to kind of finish it off, if you can imagine that overall building design as far as consumption is concerned, if you look at the consumption of the building and look at the percentages, you can imagine that how this can impact the overall building consumption and how that active design building can be really important for us. I'm going to stop in here and